Before I continue, I want to introduce you to what might be an unfamiliar concept, although if you've taken chemistry, you might know a little bit about it. It's called a mole. And this isn't the thing that grows on your face with a hair in it, or the animal that digs in your backyard, although those are also called moles. But we're talking about the SI unit called a mole. And a mole is just a number. It's like saying, a mole of something means a certain number of something, just like a dozen or I don't know what other things are that there are numbers. But it's like saying, a dozen eggs is 12 eggs, right? A dozen equals 12. Well, just like that, a mole of eggs would be 6. I always forget the exact number. It's 6.023, I think, something of that nature. You can look it up. I think it's 6.023 times 10 to the 20th. Let me look it up. Actually, the exact number, just because I think that 23. I'm misremembering. Let's see the mole. I'm on Wikipedia now, and I just looked up the mole. Okay, there you go. On Wikipedia, see, it's very useful. Oh yeah, I was close. It's 6.022. 6.022 times 10 to 23 of something. So it's a very large number of something. So normally we don't deal in moles of eggs. I don't think there have been a mole of eggs ever produced in the history of the universe. 10 to the 23 is a very, very, very large number. So where is it useful? Well, a mole is useful for counting atoms. And so what is a mole of atoms? Well, it's that or molecules. What's that many molecules? It's 6 followed by roughly 23 zeros of molecules. Very, very big number. But what's interesting about a mole is that when I have a mole of something, its mass, so let's say its mass in grams. So let's say a mole of carbon. Its mass in grams is going to be equal to, so mole of carbon, if I have a mole, so if I have this many carbon molecules, its mass in grams, it'll have x grams. It'll have a mass of x grams, where x is the atomic mass number, atomic mass of a atom of carbon. Although if I was saying about a mole of a molecule, I would figure out the atomic mass of the entire molecule. So what's an atomic mass number? Let me see if I can do a web search on a periodic table. See, I'm showing you what I do here. It's not fancy. So let me go to Google, google.com, and let's look up periodic table. Let's see if we can find a good one. Periodic table. This one looks good. Let's see what I can do. It's some time to up. Oh, no. Looks like everything is freezing up too. Oh, there you go. So periodic table of elements. Good. Let's see what we can do. So if we go to carbon, which is right here, we see that its atomic number is 6, and that's the number of protons it has. But let's see if I can zoom in on carbon. What happens? The periodic table. Oh, there you go. That's pretty neat. So the atomic mass number, it's the mass of the entire atom. And just so you know, I mean, we're kind of delving into a little bit of chemistry here, but most of the mass of an atom is the protons and the neutrons, and the protons weigh roughly the same thing, and then the electrons are much, much, much smaller. So if you pretty much factor in the mass of the protons and the neutrons, you pretty much have the mass of the particle. And then just a little more chemistry here is that although on average most of the atoms have roughly the same number of protons and neutrons, some don't. Some, you could have a carbon atom that has 7 neutrons. You could have another one that has 5, another one with 6. So and those are actually all called isotopes, and I won't go into all of that. But they're just the same atom with different numbers of neutrons. But in general, the atomic mass number, just if you had a kind of a broad rule of thumb, is equal to the atomic mass is equal to the mass of the protons and the neutrons, and they tend to be equal. So if the atomic number is 6, the atomic mass tends to be 12. So why is this useful? So we can say if we have, I don't know, what is this? Gallium. if I have a mole of gallium, right? You can, let's say niobium. Let's say I have a mole of niobium. If we look here on this on the periodic table, it has an atomic mass number of 41, and then its average atomic mass, if we were to average all of the isotopes, or kind of how based on their weighting of how they exist in nature, it's 92.9. So roughly 93. So it's actually a little bit more than double its atomic number. But let's say it's a 92 point. Let's say 93. So if we had a mole of niobium, if we had 6.022 times 10 to the 23 of niobium, it would have a mass of 92 grams. So that's pretty easy. You look at any element, molybdenum, we see here. Let's say chromium. We see its atomic mass number is roughly 52. We see that there. So if I have a mole of it, if I have 6 times 10, roughly 6 times 10 to the 23 of it, that much will have a mass of 52 grams. So that's how we think about a mole. So if I tell you I have a mole of something, I'm also telling you how many of that molecule I have, and I'm also telling you what the mass of that mole, that quantity will be, if assuming that you have a periodic table in front of you. So with that said, with that out of the way, let's make some more progress with our thermodynamics. Invert colors. So we said in the last several videos, let me see when I'm running out of time. I have plenty of time. That pressure times volume is somehow proportional. It's somehow proportional. Let's call that K. And this is an arbitrary number. It's not some special constant to the total kinetic energy total of a system. Total. And we also said that is roughly proportional. That's some constant. That's another constant. Times the number of molecules we have times the temperature, because temperature we viewed as kinetic energy per molecule, right? So in general, we could also say that this is proportional to this, which is proportional to this. That pressure times volume is proportional, and we'll use R because you'll see where that's coming from in a second. It's proportional. It's equal to some constant times the number of molecules, n. And when I write small n here, see here I was just saying the absolute number. So if I had 5 molecules, I'd put a 5 here. But now this n, I'm counting in moles. Right? So if I say if this n is 1, that means I have 6.022 times 10 to the 23 molecules. So let me see, 1 mole equals 6.022 times 10 to the 23. Right? So I'm just saying, so this is just another way to write the number of molecules, and then that's times temperature. And then if we rearrange it, PV equals nRT, we have a relationship that if I know the pressure and the volume and the number of molecules, I can figure out the temperature. Or if I know the number of molecules, the temperature, and the pressure, I can figure out the volume, assuming I know what R is. And I'm about to tell you what that is. R is called the universal gas constant, and R is 8.31 joules per mole Kelvin. And that kind of tells you what you need in this formula. This should end up being joules, right? So if you have pressure in pascals and you have volume in meters cubed, you'll end up with joules there. This should be in moles. This is 8.31 joules per mole Kelvin, and then this, as we always said, should be in Kelvin. And honestly, if you just memorize 2 things in all of thermodynamics, you'll probably be able to do 95% of problems, but you actually should have the intuition of how they work. But just remember that PV over T is equal to a constant, or that if you change them, they relate to each other, that they all equal a constant. So if P1 times V1 divided by T1 is equal to P2 times V2 divided by T2. And then you also should just need to memorize PV is equal to nRT, where R is equal to 8.31 joules per mole Kelvin. And I know you might not have a lot of intuition of this formula yet because I haven't used it, but I'm going to do that in the next video. But these are literally the two most important things you should know in thermodynamics, and hopefully you have a little intuition at this point of what they mean. See you soon.